Robot Talk is the podcast that sits down with robot enthusiasts from around the world and asks them the questions you always wanted answered. Like, is that drone walking? And how does that thing work? Hello everyone, welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is about taking inspiration from nature to design better drones. Before we get started, I'd like to invite you to join the Robot Talk community on Patreon, where I'll be sharing behind-the-scenes updates, and you can chat with me and other Robot Talk listeners. You can also sign up to support the podcast for just £5 a month. And if you do, not only will you get a warm, fuzzy feeling for helping me to keep producing and expanding the podcast, but you'll also get access to exclusive bonus episodes and lots of other cool perks. Check out patreon.com/Claire Asher to find out more. The first 20 Patreon supporters get a free sticker, so don't procrastinate, join today. So, without further ado, let's get on with this week's interview. I recently had a really interesting discussion with Jane Pauline Ramos Ramirez from Delft University of Technology about aerial robots inspired by nature. This week, I'm speaking to Jane Pauline Ramos Ramirez, a PhD researcher at Delft University of Technology, working on nature-inspired drones that can move on land and in the air. Hi Jane, lovely to have you on Robot Talk.
Thank you so much, Claire.
So you're part of the Biomorphic Intelligence Lab at TU Delft. So to get us started, can you tell us a little bit about the research that's going on in the lab?
Yes, so Biomorphic Intelligence Lab is in TU Delft, and we work on nature-inspired aerial robots that physically interact with the environment. Mm-hmm. So we use this for applications for environmental monitoring and space applications. And we use what we call embodied intelligence. So embodied intelligence takes inspiration from biology and uses that as principles for our drone designs. It ranges from sensors like acoustic sensors, hair sensors, whisker sensors, or touch sensor drones, to animal movements such as locomotion. So that's my topic. And for example, use of manipulators or grippers such as perching on branches or stuff like that for environmental monitoring.
Cool. I'm particularly interested in bio-inspired robotics. So I'm very excited to talk to you more about your drones. So yeah, I mean, as you mentioned, you're working on the locomotion side of bio-inspired drones. Can you tell us a little bit about the drone you're working on?
Yes, so it hasn't been published yet, but I'm working on a flying and moving on ground drone, where the locomotion on the ground is quite versatile because I'm using compliant limbs for movement on the ground. So the locomotion is quite novel, but it's quite a rolling locomotion.
Okay. And the idea as well, I guess, with the kind of the soft limbs is that you can have quite a gentle landing like a bird would.
Yes. Yeah, so this one we published that we use this compliant landing gears on a drone or on conventional quadcopter, and we found out that it decreases the landing mistakes of a drone as compared to the rigid landing gears.
Mm-hmm. Okay. And so can you talk a little bit about the challenges of designing robots to kind of handle these two different modes of movement?
Yes, so the biggest challenge is that the movement on flight and ground have very conflicting design requirements. So first off, for flight, you really need to keep everything lightweight because you want to fly, right? So if you're sharing actuators, you need high frequency for the flight, but on the ground, you need high torque. So to overcome obstacles or to move on unstructured terrains, for example, you really need high torque. So those are like the trade-offs in the mechanical design itself. And to seamlessly transition from flying on moving, it's not just about the mechanical design, but you have to integrate the whole design process holistically. So I have to think about like, okay, I'm designing this and eventually I need to manufacture this and I need to control this. So I need to really look forward and backward all the time. And test in the middle of it if it actually works or not.
Yeah.
Because the manufacturing will affect sensing, will affect control, and then eventually you want to interact with the environment. So in the field, we practically don't know what will happen in real life.
Yeah.
So you really need to test it. And each phase is a very non-linear process. You really just need to test it, accept that it will fail or it will break. And then I really need to dig deeper on my curiosity and my motivation, because failures is part of the process. And when you do manufacturing and testing on your own, you have to be okay with things breaking and testing and rebuilding multiple times.
But that feeling when it works must be fantastic.
It is. But since we are doing the PhD, right, you don't really achieve the technological readiness level of something that you can sell it to people for commercial use. So yeah, definitely things break. So
yeah.
But it is fantastic to see it actually moving when you're testing it.
Yeah, absolutely. Talking about, robots that can move in the air and on land, I guess if I think about birds flying, quite often their legs are kind of awkward in flight. They have to kind of tuck them behind them. They're like,
yes.
Is that a problem you've come across trying to make drones that can walk?
Definitely. I mean, I would frame this as a problem on how to not use the ground locomotion systems and hinder the aerodynamic side in flight.
Exactly, yeah.
Yes. In birds, right, they don't really like fully moor, but they actually make it more aerodynamic by maybe putting it in the backside so that it doesn't block so much and create so much drag. Yeah, definitely the mechanism to morph or transform these ground locomotion systems is a challenge. But it's also, for me, it's a challenging way to think creatively.
Yeah.
Especially for using soft robotics, because I think this is what soft robotics offers as a novel way to approach things. Because when you have fully rigid components in your robot, it is actually less safe, for example, when it interacts with the environment.
Yeah.
But for soft materials or soft components, they are able to accept more impact, for example, or they just bend or deform to adapt to their environment. So for me, it's more versatile. It's also more complex and more unpredictable. But it's a good way to stretch your creativity, I think.
Yeah, absolutely.
I mean, soft robotics is a very young field, and there are a lot of ways you could extend it or investigate it more. I'm quite interested in how the field would come over the years in the future.
Yeah, definitely. Me too. It's been really interesting to see how it's developing so far. I think it's interesting because you mentioned that the drone you're working on at the moment, when it's on land, it has a rolling motion.
Yeah.
Which is not like anything that any animal does.
Yes.
Yeah, bio-inspired, but not biomimicry, I guess.
Exactly. Yeah, exactly. So biomimicry is exactly copying what nature has and translating that to designs in robotics, for example. But bio-inspiration is just using the principles of nature and applying that to robots.
Yeah.
I don't think we can fully mimic yet because of our technological limitations. There are a lot of limitations for miniaturization and actuation and power density. So how do we deliver power?
Yeah. So you mentioned two different application areas that the lab is working on in general. You mentioned environmental monitoring and then also space exploration. So is that your goal for the flying and walking robots, or are there other application areas you think that kind of design could be suited to?
Yes, in a practical sense, I would like it to be contributing towards climate transition and environmental monitoring, or maybe interacting with the environment to do something for the communities. Other than monitoring, maybe mitigating effects of climate. I don't know yet, but currently I want to contribute on that.
Okay.
So on a high level sense, the application for drones that do multimodal locomotion, I feel like they're good for improving the endurance of robots. So extending the operational space, not just on how far they can go in terms of area, but the kinds of environments that they can operate in. Right. Yeah. So you can fly long distances, for example, and if you encounter some kind of obstacle, then you can switch to ground locomotion. It's easier to move on the ground when the space is too low or tight or cluttered for flight. And another application on a high level is maybe extending the versatility of robots, right? Because as you mentioned, animals they can use the limbs that you said that they tuck in for flight. They can also use this for eating, for example, or manipulating their prey. So they're very multifunctional. So what I want to do actually in my drone right now is to instead of building separate systems for each task, I want to try to reuse the same in some kind of a clever way, right? So of course, this adds to the complexity of the system, but hopefully it will result to something that is more adaptable and more capable in real-world scenarios. But it needs a lot of experimentation and testing and rebuilding and testing.
Of course, yeah. But yeah, I guess the more adaptable and versatile you can make it, then the kind of the more different application areas it could be used for.
Yeah, hopefully, exactly.
So we had an audience question submitted by Jonathan on the website. Jonathan says, can we make flying robots more efficient by taking inspiration from nature? And if so, what is the best form? He then had a follow-up, which was, what are the pros and cons of taking inspiration from nature?
Yeah. So what do we mean by efficiency, actually? If we're talking about power efficiency, then yes, nature has a lot to teach us. We can draw inspiration on how animals process information, for example, or how we structure the bodies, design the mechanical system to make movement more energy efficient. This can lead to smarter, more power-efficient designs and better overall performance. And like as I said, we can also extend functionality through bioinspiration. So for birds, right, they do maneuvers that are very complex or aggressive flight. So for example, they soar and then they change forms. And for robots, for example, fixed-wing drones, the drones that don't have propellers, they can perform sharp maneuvers at various speeds, for example, by morphing their wings. And these are guided by bird flight experiments or investigations on birds. But on the question of the best form, right? I don't think there is really one, or at the best of my knowledge. It really depends on the application that you really want to approach, the research question that you want to ask. Yeah, so some of the work are curiosity-driven, others are very specific for a certain application. But researchers are still trying to investigate and learn new strategies on how to design these systems. And how do animals actually do this in the first place? We don't fully understand them, the full mechanics of how they interact with the environments. And that is something that it makes us curious, right, as a scientist.
Yeah, absolutely.
And there's still a lot of gap in the knowledge. And then the question on the pros and cons. So this is my personal belief that The pro or the advantage of taking inspiration from nature creates a deeper connection and deeper understanding on how we interact with the natural world. So when we study how animals move, how plants sense, how animals solve problems, it's quite fascinating. And this fascination can inspire us to be more mindful about sustainability in our design and how to preserve these species that we're taking inspiration from. And there's actually a term for robotics now. It's called sustainable robotics. And this is covering somewhat like in this direction, how bio-inspired robotics can be useful for environmental preservation and environmental conservation. And another pro, maybe it's just a personal thing, is it's fun, right? You observe nature, it's meditative, and you draw inspiration for something that has evolved for so many thousands of years, and you try to translate that in a very simplistic way on a robot that you're working on, and eventually it will work. It's quite fun and a satisfying process. One con that I thought about, or limitation, I have also talked about this a while ago, is that we cannot really maybe compare directly what animal performance is with our robot performance. We can compare one parameter, several parameters, but we are really limited of how we understand nature, first of all, and how the current technology is, right? So sensing, it's not as good as the hairs of animals. It's not as good as how they translate their energy from what they eat to their movement, so actuation. And even how they process the stimuli from the environment, how they, from the sensors, they get the stimuli information from this, and how they process in computation, how their brains work and how their bodies work together with it. So for me, it is possible to compare some parameters of the performance, but not exactly the whole versatility of how animal can perform tasks and how they live and how they interact with the world.
Yeah, I guess that's the difference between bioinspiration and biomimicry. If you was to say, right, I'm going to make a robot peregrine falcon and I'm going to try and perfectly mimic this bird, then theoretically you could directly compare what you've done to the peregrine falcon. But when you're taking kind of inspiration from nature more generally, like you said, you can't, there is no direct way to compare what you've made to what nature has made.
Right. But also, for example, biomimicry, you can make a bird that is exactly like this falcon. Yes, you can assess the performance with it at flight, but what about the bird that can actually adapt to different obstacles or different interactions? Well, you need to program that with how the robot is able to do that. But yeah, we're very far off from like animal performance, I would say.
Yeah, absolutely. So I think, as you mentioned earlier, a higher level goal of yours is to develop robots that work in synergy with nature and also create meaningful impact for communities. So what characteristics do you think robot systems need to have to achieve those goals?
So for me, this really comes down to awareness and intention, both in the design process and in how technology is applied, right? I want to create robots to have a meaningful impact to communities, which is why we focus on areas like environmental monitoring, for example.
Yeah.
And there's this concept called design for values. I don't know if you're familiar with that.
No.
But I find it really important because it says that you integrate moral and social values like justice, autonomy, and sustainability into the design process, which is quite a daunting thing to do as a roboticist, for example.
Yeah.
How do we even begin, right? But the importance is we ask these questions from the beginning, and we can create these technologies that are not only technologically sound or excellent, but also relatively more socially accepted. Yeah, because they reflect the needs and values of the people they're meant to serve, which is quite it's hard to maybe think about it in an engineering perspective, but the fact that we're questioning, the fact that we're asking, right? I think that's a very useful thing to do. Like I see that the robotic system can also include the user and the technologist as part of the system as a whole.
Yeah.
So the technologist might design a certain goal or application in mind, but ultimately it's the user who decides how the technology is applied. So one characteristic that these system needs is a really continuous dialogue between both sides, right? A process that includes checks and balances and builds trust and accountability in how technology is applied to real life. And another characteristic is respect and curiosity. So how we relate to each other, but to the environment and other living things, not just humans, right? What kind of values are we embedding in our technology and how it is communicated to society? Like for academics, you publish papers, but how do you actually communicate that to people in need of your technology? What kind of future are we working toward, and how we can use robotics to ask better questions, like how we work together to save lives, support communities, and leave a better planet for the next generation, which is big questions, right?
Yeah,
but the fact that we're asking it, the fact that we're talking about it, I think that's the most important part, the curiosity and awareness. Yeah, that's one of the things that's I try my best to carry into my own work.
Yeah.
But it leaves me asking all the time, right? Like, am I actually contributing something, especially if I'm faced with something really hard, with like hardware issues or something? And how do I relate that to the bigger vision? How do I relate that to the bigger picture? So we're developing this multifunctional system inspired by nature, designed for applications like environmental monitoring. But I also try to do something else to like broaden my vision. So, for example, diversity and inclusion initiatives. Like we had a recent event where it's called the Girls' Day, where we invite girls into the labs, show them how the labs work. We create a day where they can just investigate on their own and see role models for themselves. See them as part of the future that we the current generation are building. And the goal is to just not make robotics as something that is technically excellent, but it's also socially meaningful. Another thing that is very close to my heart is recently I worked with the Dutch Climate Research Initiative and the Thrive Institute. We were investigating the pilot projects in the Netherlands for climate transition. And it's an interdisciplinary team of PhD students all over the Netherlands. And we look into the pilot projects in healthcare, agriculture, and energy, as well as like systemic approaches. And these projects don't just create direct impact, but they offer real insights into what's needed for the change that we are trying to build as technologists. And I think there's no like one way to answer this, but it's just it's all come together. We just try to make the best out of our visions and our work, and hopefully it creates ripples to change for the future.
Yeah, absolutely. I mean, it's a lot to try and keep in mind all at the same time. But like you said, just kind of having that awareness and asking those questions is really important. I had a really interesting conversation recently with Patrick Meyer, who runs the Climate Robotics Network.
Oh, yeah, I've met him.
Really, really interesting work that he's doing.
Yeah, it was, I think, last year that I participated in a conference. It was a really enriching discussion. We talked about aerial robotics. There's also other topics like marine robotics and stuff like that. How robotics actually contribute to the climate transition with startups and researchers and really cool work. This is really truly something that you see the social impact of your technology, and it's heartwarming.
Yeah, definitely. I mean, you were talking about embedding the values, like societal values, and kind of meeting the needs of the users. Is that harder when you're doing more curiosity-driven research that's less application-driven? Because if you don't quite yet know who the user's going to be, it's harder, I guess, to embed them in that process.
Yes, definitely. I think what I can do for this is the communication process, right? How do you frame the technology that you're using? How do you create scenarios that that show its capabilities in a way that it would be relatable to people?
Yeah.
And of course, curiosity-driven research is something that is really hard to connect to, especially if you're outside the field.
Yeah.
But that's how we relate as humans, right? We talk about it. We talk about it in stories and anecdotes in a way that you can relate. Each other will try to understand just a little bit, or the big picture of it.
Yeah. Jane, it's been lovely chatting to you today. I've been talking to Jane Pauline Ramos Ramirez from Delft University of Technology. Thank you.
Thank you so much.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. It really helps boost the podcast, so thanks in advance. And make sure you check out @Robot Talk Pod on social media to see a photo of a drone with flexible arms that can land on uneven terrain, which Jane and I talked about. Next week, I'll be talking to Nick Thompson from Bow about standardising robot programming. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk is brought to you by the Hamlin Centre, Imperial College London.